Two-sided marketplaces are a great way to resolve supply and demand inefficiencies. There is such high demand for great programmers, but there is only a limited supply. So why would it make sense for a great developer to use a terrible tool like a job search engine? That's why I love Hired.com. Developers can sign up at hired.com/softwareengineeringdaily and be connected with 5 great job opportunities at companies like Stripe, Uber, and Facebook. If you're a developer, you shouldn't settle for a mediocre job. I know this from personal experience. It will stunt your career growth. Hired will give you a $2,000 bonus if you find a job. And if you go to hired.com/softwareengineeringdaily, you will get an additional $2,000. It costs you nothing to try it out, and it's a fun process. I urge you to try it out. Distributed applications are moving towards a model of increased real-time streaming. Neha Narkhede is the co-founder and CTO at Confluent, which provides Apache Kafka as a service. She formerly worked at LinkedIn, building systems with Apache Kafka. Neha, welcome to Software Engineering Daily.
Thank you, Jeff.
So we've done a show about Kafka with your colleague, Guozhang Wang. If listeners want an overview of Kafka, they can check out that episode. But we should still give some context around Kafka. I mean, I'd like this episode to be more of an advanced Kafka or applications of Kafka episode. But just for people who need a refresher, let's start with some background. Why was Kafka originally developed?
Kafka was originally developed to solve a very key data flow problem at LinkedIn. 5 years ago, when I joined LinkedIn, we were struggling to get access to all our data, and we were rapidly developing newer products that needed real-time access to data. And there were two sort of trends that we were struggling with. First, the diversity and number of systems that we were putting to practice was increasing. The old workhorses like MySQL and Oracle still existed, but they were complemented by new specialized distributed data systems like, Walmart and Redis and Hadoop. And each were built for a specific purpose. The second trend was that the diversity and size of data that we wanted to collect was increasing. We were going beyond collecting just database transactional data to log data, system metrics. And so, both of these trends were creating a big problem for us to get a unified access to data. And the problem was really the systems that we were using were very bifurcated. We had ActiveMQ, which was a sort of older enterprise messaging system that is real time but couldn't scale, and we had sort of these one-off ETL tools which could scale but were not real time. So Kafka was sort of created to be a single infrastructure solution for a centralized data pipeline at LinkedIn.
Once you had Kafka developed, how did it change the way that engineering worked at LinkedIn?
It changed it in a number of different ways. Firstly, access to data wasn't a big research project. Product development could continue painlessly because Kafka just made any new data source in the company available painlessly. The second was, scale. The amount of data that we could tap into to learn how users were using LinkedIn or to monitor the health of the website, we could handle that scale very easily. In fact, today, Kafka serves more than 1 trillion messages per day at LinkedIn. And the third is really, there was a big push towards stream processing, which was possible because of Kafka. Kafka offers a variety of primitives that are essential to scalable real-time stream processing. So a lot of our, workloads that were initially run on the warehouse or on the Hadoop side could gradually move to a more stream processing sort of style of processing.
Kafka is described as publish, subscribe messaging rethought as a distributed commit log. At least that was the original description. If you were describing Kafka today, would you change anything about that definition?
Not really. It is true that sort of Kafka was started as a pub/sub messaging system, and gradually we architected it to become this distributed commit log. And the goal was really to solve this real-time data integration problem as a fundamental infrastructure problem rather than a tooling one. And that required a central infrastructure to, scale efficiently, to be real time, as well as have, inbuilt replication and durability. So you can, send all your important as well as large scale data sets through it without worrying about operations.
Yeah, and speaking of this real-time data integration, when I was preparing for this interview, I watched a video, which I will put in the show notes, called Real-Time Processing at Scale. It was a talk that you gave at Airbnb, and it was really good. In that video, so in that video, there was one problem space that you discussed relating to Kafka, and that is this real-time data integration. So just so we can put a finer point on this, can you define real-time data integration and give an example?
Sure. By data integration, and it is a commonly overloaded term, I meant the ability to collect data from several disparate sources and making it available to all your systems and applications that need to process it. In fact, recently, Martin Kleppman, my colleague, he used an interesting term to describe this. He called it data liberation, which is probably more apt. And the problem is that traditionally data integration has been treated as a tooling problem. One-off ETL tools are jerry-rigged together to make data available. And more often than not, it is done in batches, maybe once or a couple times a day. But today, there is an increasing need for not just solving the problem of data integration, which is making data available, but also making a transition to real-time data. So by real-time data integration, I just mean the ability to integrate data from several sources and making it available in real time easily to various applications that need to process it.
So an example from your LinkedIn days might be when a user updates a profile, that update needs to be visible to newsfeed, to search,
That's right,
to all these other aspects of the website.
That's right. And that's a great example. You update your profile, the newsfeed systems need to process it so your update can be visible to your network. The search systems need to process the same update and index it so your profile is searchable on new attributes. And the same, event needs to go to Hadoop for analytics. So it's the same data is consumed multiple times and projected in different derived views.
And before Kafka, how did LinkedIn maintain consistency between these different services?
That's a great question. We really didn't. In fact, consistency and operability were two big problems. Prior to Kafka, essentially data integration was done by duct taping several tools together to get data to flow between different systems. And the problem was that with every new data source and with every new system that we were rapidly adopting, we had to manually fix all this different tooling to get the new data source integrated properly. The problem with that approach is it might work early on, but it just turns into an operational mess. And above everything, it doesn't give you a consistent, unified view of your data. Most importantly for us, it really slows down product development. So that was a big impact.
So what do you think it was about LinkedIn's set of problems that made LinkedIn the one to develop Kafka? Because I feel like, so many people have adopted Kafka since then. It seems like it's a problem that so many people had and still have. It could have come from anywhere. Why do you think it came from LinkedIn?
I guess partly opportunity and partly, LinkedIn's engineering focus and sort of openness to open source. I think really back then when LinkedIn experienced this problem, a lot of web companies were experiencing the same problem. And the problem is essentially of scale. And that is what was different about LinkedIn's sort of problem with data integration. Now this is becoming much more commonplace in companies where companies are turning around to being more data oriented. But the thing that stands out about LinkedIn is that LinkedIn has been a very data oriented company from the very beginning and very engineering engineering focused. So that created sort of a culture and opportunity for some of us to tackle this problem. But if I remember correctly, it wasn't a very sexy problem that any engineer wanted to deal with. A couple of us did get together because clearly it was a problem that would create a big impact towards how fast we could move as a company.
When Kafka was introduced to the distributed architecture at LinkedIn, the goal was, as you said, to make it a centralized pub/sub service that all the major application components communicate with. What were the architectural changes that had to be made to allow for this shift?
We decided to incrementally onboard existing data pipelines on it, instead of doing a large big bang cutover. And the purpose was to take time and work on operational improvement and stability that might have gotten uncovered with early usage of the system. So that was very important for us with Kafka in the early days. And that is essentially sort of the reason for Kafka's success is that it is operationally simple and it just works. So we started by collecting user activity data for analysis in Hadoop, and then moved over our entire monitoring pipeline to collect metrics through Kafka. Later on, we built replication as a first-class ability within Kafka, so we could send database change logs and, more important, messaging type data through Kafka. In fact, today, now, all of LinkedIn's data pipeline runs off Kafka. All the products and systems, including the warehouse, taps into the same Kafka pipeline to get access to data. And it has grown, sort of gradually over the years.
In an application architecture that uses Kafka, every application component is either a producer, a consumer, or a broker. And in that video where you were talking at Airbnb, you mentioned that at LinkedIn, there are tens of thousands of data producers, but only thousands of consumers. Why is there such a large difference in volume between producers and consumers?
The difference is, in terms of number of instances, but not so much in the read versus write ratio. So to elaborate, every single machine at LinkedIn is a producer and sends data to Kafka. And this data could be, machine metrics and application metrics data, plus any kind of application messaging data, while consumers are really tied to downstream applications and systems. So due to that, purely in terms of number of instances, it seems that there are more producers than consumers. But in terms of volume or the data or read-write ratio, typically every message that is ever produced is usually consumed roughly 4 to 5 times downstream. Like in the LinkedIn example I gave earlier, one profile update is consumed multiple times by different systems to process it differently.
And in a Kafka deployment, a cluster of brokers sits between the producers and consumers. As I mentioned in the last question, can you give some more color on the role of brokers? What is the purpose of a broker?
The brokers, decouple the producers from the consumers by acting as essentially a persistent buffer for data. So the key difference between Kafka and other messaging systems is that it has persistence built in as a first-class capability versus an option that you can just turn on later. Another key difference is that message retention is not tied to consumption, and that is very different about Kafka's broker design. And that ability allows systems with variable consumption profiles to consume from the same topic in Kafka without performance degradation. So you can attach a monitoring system that consumes in real time the same data, and you can attach Hadoop that consumes maybe several times a day or every couple of hours without worrying about performance, which is a huge sort of difference between other messaging systems and Kafka.
The brokers are negotiating the message passing between the producers and the consumers. Under what circumstances would the brokers need to scale?
Producer and consumer throughput, as well as scalability, is really tied to partitions in Kafka. So every broker, it hosts a certain number of partitions or shards for your topics. And as producer and consumer throughput increases and the live traffic increases, you either increase the number of these shards so you can write to more in parallel, or spread the existing shards over a larger number of brokers so you get more bandwidth. And so essentially it is a function of sort of the producer and consumer throughput as well as partitions in a cluster.
Great. And if listeners want to hear more about that, they can listen back to the interview I did with Guozhang about Kafka. So when people hear the description of Kafka as a distributed commit log, they might be thinking of something like Apache web server logs, but that's not really what you mean. The Kafka log is more like a general data structure. Can you describe the properties of the Kafka log data structure?
Sure. And this is, a great question. This log is the central abstraction that Kafka provides. And as you correctly clarified, a log is really an abstract data structure that has some properties. It is like a structured array or a feed of messages or data. So data is always ordered. It is append only and hence immutable. So the records don't change once they are written. And records are ordered by time. So newer records are appended to the end of the log. And the most important thing is that each record is addressable using an index, just like an array. It is sometimes known as the log sequence number, or in Kafka, we call it an offset. And each record in this log has some data that is just some byte array that can be serialized using one of the many serialization formats, whether it's JSON or Avro or protobuf. Essentially, this commit log abstraction is what gives Kafka high performance that it supports.
When you were designing Kafka, were there any other types of data structures that you considered? How did you end up with this log structure?
Back then when we, before we designed Kafka, we were struggling to use other messaging systems. And what we observed was that a lot of other systems, they structured data as a traditional sort of B tree. And the problem with that is it doesn't quite exactly match the access pattern that you want for pub subsystems. If you look at pub subsystems, the access patterns are naturally sequential. You read data, which is append only, and then you write data that is, you read data that is sequential and you write that is append only. And so what we observed was that the best data structure would be one that optimizes performance for sequential access. And that is essentially this write-ahead commit log. And the second reason is a little more subtle. We realized from our earlier attempts of using older systems is that consumption needs to be rewindable. It doesn't work to delete messages when a certain consumer has consumed it because the downstream systems can fail or applications can have bugs. So you have to have the ability to go back and reconsume past data. So this log data structure allows that very naturally by allowing consumers to maintain an offset and rewind to a certain position in the log to read ahead from there.
So that sounds pretty expensive. How does Kafka do garbage collection on messages?
That's a great question. There are three ways of doing garbage collection in Kafka, and the first two are really easy to understand. One is, time-based garbage collection. Here, you configure your topic with some time window, let's say a week or two, and you can always maintain larger time windows as long as you have space because performance is decoupled from retention. The other one is also straightforward. It is space. You can configure it to just maintain a terabyte of data and it garbage collects older data. The third one is a little more nuanced and is very special to Kafka. And that is what makes Kafka more like a commit log or a database, which is really a garbage collection policy called Compaction. So let me elaborate. Every message in Kafka, it has a key as well as a payload. And Kafka has the ability to compact and garbage collect data in a log. So older values for a particular key can be garbage collected, leaving only the latest value. And if you use this capability, then you essentially have the commit log of a database, because the log has every key and that was ever written to the database, and it maintains only the latest value. So you can sort of reconstruct your external database or a cache or your RocksDB instance by just reading from this compacted log from offset 0. So depending on your application, you use one of the 3 garbage collection policies in Kafka.
So for people who are listening who may not have a great grasp of how Kafka works, is Kafka one giant log with all the messages, or are there a number of different logs across a Kafka deployment?
So Kafka, data is organized in partitions, and every partition has this conceptual write-ahead log. Underneath the covers, there are several physical log files that compose a write-ahead log, where all but the latest log file are read-only and immutable. So as you write data and as log files reach a certain size, they are rolled over to become read-only, and new ones are created.
Are there any best practices for when a user should be creating a partition? Like, is there like a one-to-one mapping between partitions and services, or how does that work?
Partitions are, usually sort of, they scale with the amount of data. So what users deal with is conceptually a topic, but then you assign a certain number of partitions. You mostly over partition your data to be able to do parallel reads and writes.
Got it. Kafka enforces a strict ordering on messages. Do you use vector clocks for this?
Not really. So Kafka provides ordering guarantees at the partition level per producer instance, and messages are assigned to partitions based on a key that, as I mentioned, every message has. So what happens is all the data for a particular key from a particular producer ends up in the same partition, and hence all the data for a key is strictly ordered. So Kafka does not attempt to imply ordering of data across producer instances just yet, So it doesn't use vector clocks, but the brokers have an internal notion of logical time that is dictated by the offset. So every partition's log, like I mentioned earlier, it has the notion of an offset that starts at 0 and increments every time a message is written to the log. This offset applies the notion of time to the log. So when a message with offset 10 is consumed, it can only be consumed after a message with offsets 5 and so on.
Got it. So Kafka provides many of the guarantees of a database. Messages are strictly ordered and all of the data is persistent. Could you describe that persistence model in more detail and maybe explore how it compares to a database?
Sure. Kafka is a distributed commit log, and if you observe, that is the data structure that a database uses under the cover. So a database typically maintains a redo log that it uses, which is really the source of truth. So if there are problems, then it uses that log to recover itself. So in order to do that, what you need is the ability to maintain the latest sort of value for every row or every key that your database has. So that is sort of the, if you look at it closely, you can draw the parallels between a database commit log and Kafka with log compaction that I mentioned earlier, because what it gives you is the ability to maintain every key or every row in your database while garbage collecting older values. Because when let's say you get a key from the database, it doesn't give you all the values, it only gives you the latest value. So this log with log compaction, it allows you to essentially do that. Every row that you have in your database is present in the log. And so if you wanted to reconstruct your database, all you do is you read through this compacted log from offset 0 and you create your derived view. The derived view could be anything. It could be a search index, it could be a RocksDB instance, or it could be some other cache. That is really the power of this commit log idea, is that it has a source of truth and it allows you to create different derived views based on your application needs.
I saw you speak at QCon San Francisco recently, and I will put that talk in the show notes. It was really enjoyable.
Thank you.
It was called Demystifying Stream Processing with Apache Kafka. And by the way, it had these really nice like watercolor diagrams.
Paper.
What'd you say?
It was created using this app called Paper, and it's in fact a commonly asked question, so I clarified that early on.
Yeah, it was great design. So anyway, it was called Demystifying Stream Processing with Apache Kafka. What are the aspects of Kafka that people need to have demystified?
My talk was about demystifying what stream processing means and how Kafka has inbuilt primitives that make stream processing much simpler and easier to use. That was the focus of my QCon talk, but the other aspects of Kafka that are now somewhat demystified over the years is that it is really, this commit log under the veil of a sub-messaging system, and the way it should be used is as a central sort of data pipeline and source of truth for all the data in your organization.
Right. And one thing you said is that stream processing is not necessarily transient, approximate, or lossy. Why did you have this slide?
I included that since I observed that this is a very commonly misunderstood notion about stream processing. And that is that in order to get faster results, you somehow need to give up correctness or introduce lossiness. A lot of stream processing systems have been that way, but the reason for that is a weakness of that system and not an inherent property of the stream processing paradigm. My claim is that if properly designed, you can absolutely make stream processing systems compute accurate results, just like batch systems can do, as well as do that efficiently.
And you described a spectrum of trade-offs between latency, cost, and correctness. Can you describe how can we explore the different points along that spectrum?
Most systems are trying to design specifically to optimize for some of those trade-offs at the cost of others. So, more precisely, systems are giving up correctness for latency. And I'm arguing that stream processing systems have to be designed to allow the user to pick the trade-offs that the application needs. And I'm saying that because stream processing covers a very wide range of needs, and every application is different. So for instance, some applications care about correctness, like billing, while some may not have to, like log processing. Some applications might need to be low latency, like alerting, while some may not have to, like ETL. While other applications might actually be okay with the cost required to optimize fully along the other two dimensions. So this is really, a choice that an application writer or application designer should make, and not the stream processing system itself.
Over Thanksgiving, I had a great idea for a web app. So instead of spending time with my family, I locked myself in a room and I started building this application using Express.js because I love full stack JavaScript. So I was testing my application locally and I was making great progress. So I decided to deploy it and share it with some of my friends and get some feedback. I used DigitalOcean. I signed up for an account using promo code SEDaily, and in 15 minutes, I had my app deployed to a server and running. It was that simple. This was really the first time I had used DigitalOcean. So if you're like me and you like building stuff and you have ideas for projects, give DigitalOcean a shot. It is the fastest and simplest way to deploy an application that I've ever used. If you want to give it a try, go to DigitalOcean.com and use the promo code SEDaily to get $10 in free credits. Check it out. You said that the hardest part of distributed systems is not coding. and it isn't debugging. It's actually operations. Why is operations the hardest part of distributed systems?
That code is essentially an extension of Brian Kernighan's code. He said, everyone knows that debugging is twice as hard as writing a program in the first place. So if you're as clever as you can be when you write code, how will you ever debug it? I really extended it based on my experience to add that operations is much harder than coding and debugging. And I said that because I think the success of distributed systems should be measured by the ease of ongoing operational simplicity. Every single capability should be designed keeping operational simplicity in mind. And that is because distributed systems, consist of several components that fail very often. And those are often very tricky partial failures. While the expectation is to preserve all the guarantees while recovering from failures as if they never happened. Even simple things like the concept of time is not consistent across the board. So writing robust and operable distributed systems is several times harder than writing, robust single machine systems. My experience has been that the effort and time required to make a system operable under all circumstances is several times larger than the effort required to add a feature or troubleshoot it somehow.
Let's talk a little bit more about those failures and fault tolerance. What are some common failure cases that can occur during using streaming like in Apache Kafka, and how does Kafka handle those with fault tolerance?
What common failures are, failures that happen in most data centers. So, machines fail, you have disk failures. And Kafka, the way it handles that is, the idea of replication is inbuilt. When you write a message, you can pick the number of replicas that the message should hit before it is considered to be fully committed. And Kafka's sort of durability and fault tolerance guarantees are very interesting. Kafka is a very general purpose system, so it has a variety of different applications that can use it. So on one hand, you can have log processing applications that, want to optimize for availability while giving up consistency. While on the other hand, you can have applications like messaging or billing that really need high durability and they can give up availability. So Kafka, the fault tolerance guarantees are designed so that applications can pick whether they want to make it behave more like an AP system and optimize for availability or more like a CP system and optimize for consistency.
So, and there you're talking about the CAP theorem for listeners who didn't pick up the CP versus AP. Yeah, interesting. Does the idea of a pub sub log system? I guess that maps. That was actually going to be my next question. That maps well enough to the ideas of a database that you can just think of Kafka just in the domain of the CAP theorem.
Yeah, like I mentioned, it's a pub subsystem, but it's really like a system of record. And depending on your application, your system of record either needs to optimize for staying available all the time in the presence of failures, or taking a hit on availability while maintaining full consistency, right? So it's really a spectrum of needs, and Kafka is designed to address a very large spectrum of application. Hence, it sort of provides you the knobs to sort of tune it to behave either like one versus the other.
So one thing that I think could certainly use some demystification is something you had a slide about. You said logs unify batch and stream processing. We've done several shows on Software Engineering Daily that have touched on this batch versus stream processing. Could you elaborate on this? How do logs unify batch and stream processing?
That's a great question. So if you think about sort of this log data structure, or if you can just, it's hard to imagine, but just imagine an array of messages. If you think about what batch systems do, right? They wake up and they, let's say, start at 0 and process a couple of messages before they reach the current end of the log, and then they go back to sleep. And then they're scheduled to wake up at another time and continue from wherever they left off and do the same, right? And so they keep repeating that. And if you look at if you look at history, batch systems have been used to process unbounded data sets in this way since several years. If you look at stream processing, the only difference is it is a process that when it starts at a certain position in this log, it consumes until it reaches the current end. Instead of going back to sleep, it just continues to wait until new data comes in and it keeps processing data. So really, that is a very subtle difference between what stream processing a process could do and what a batch process could do. So it's in fact log sort of unifies that because it's a very small behavioral difference. You can tune your application to either behave more like a batch system and sort of optimize for throughput, or you can make it to behave like a traditional stream processor and optimize for latency and keep waiting and processing data as it arrives. So this log data structure, that is the reason I think that it actually unifies these two processing paradigms, blurring the lines between stream and batch and letting a new paradigm for data processing emerge, which currently doesn't have a clear name.
Oh, that's super interesting. I mean, can you talk? So do you think that this idea that we have, where there's like a gradient between batch and stream or real time processing, this is like a false dichotomy, and actually we need a totally different model?
Absolutely. It is a sort of dichotomy that is created because of implementation details of existing systems. And if you zoom out and look at the sort of log view of things, then there really isn't a major difference. It's really a knob that you tune to make a process behave one way versus the other. And it requires a sort of, designing it almost like inside out and rethinking about the entire data processing space a little differently, keeping existing systems, out of the picture. And that is where this insight comes from, is really like our experience of looking at this log and realizing that, well, this isn't really a very different thing, and stream and batch are just two sides of the same coin.
So I think maybe this brings us to the kind of back and forth discussion that I've seen between Jay Kreps, who works with you on Kafka, and Nathan Martz, who originated he's the author of Apache Storm, and he originated the idea of the Lambda architecture. There's kind of an ongoing debate between this idea of the Lambda architecture and I think what Kreps calls the Kappa architecture. Is that
That's
what he
right.
calls it?
The debate is about how to cover the entire sort of data processing space, which is now moving more and more to lower latency processing, right? The Lambda architecture, sort of the argument there is traditional stream processing systems don't cover the entire range of needs, and you somehow have to sort of complement the stream processing system with Hadoop or a batch processing system so that it can go back and reprocess data. And the real argument is only about reprocessing data, because stream processing systems don't really allow you to do that. They don't give you the primitives, the existing ones. And so what that creates a need for is a batch system to allow you to go back and process historical data. And the need for historical data analysis is many times, right? So you can have a bug in your application, or you just need to version your application. So if you're creating an external view of your data, then you have to go back and reprocess data so it reflects your current code. And the Lambda architecture, the way it solves is it by using several different infrastructure components. One is a stream processing system for current data analysis, and the other is Hadoop for past data analysis. And the sort of the Kappa architecture argument is that, well, that's a really complicated automated way to process your data, and all you need is the ability to reprocess data, and that is something that your sort of your underlying commit log should provide, or your stream processing system should expose. And that is the argument that we're making with Kafka, is that Kafka has this log data structure. It allows you to reprocess data, and if you had sort of a stream processing layer on top, it could expose the same primitives, and hence you run a much simpler application architecture where you don't need an external system like Hadoop to complement that need.
Very interesting. And so one thing from your talk that at the time I didn't really understand, and I think it would be really useful if you could discuss. So I think this gets to talking about the interface between Kafka and the data sources or the data sinks, and Kafka Connect supplies an interface. Can you talk about what Kafka Connect does and why it is so important?
Yeah, so taking a step back, there are really two parts to making the shift to real-time data and processing, which is something we're interested in. One is, how do you get data from existing systems into Kafka, And the second one is, once you have all your data, then how do you process it to really get value out of it? So to that effect, the first problem is solved by Kafka Connect. The goal is to facilitate large-scale real-time data import and export for Kafka. And the reason, sort of the motivation behind it, is that, over time, Kafka has become tremendously popular to enable streaming data flow between external systems. And the open source community over time has written, many different connectors to integrate Kafka with existing systems. But our observation has been that every tool looks different. It doesn't solve all the problems that need to be addressed for reliable large-scale data ingestion. So users are forced to understand many different tools, and there isn't a single way of importing and exporting data on top of Kafka. And to address that, we released Kafka Connect as part of the latest release of Kafka. And the goal is really to make it easier for users to, sort of import data without writing code. And so that is the problem that Kafka Connect aims to solve. And we want to work with the open source community to create a very rich ecosystem of connectors that could just, you can just plug in and get your data to flow between various databases into Hadoop and other monitoring systems.
What about Kafka Streams? What are Kafka Streams?
That is really the second part of the problem I described, is once you have data to flow, right, between all your systems in real time, the next problem you want to solve is processing. And Kafka Streams is essentially a lightweight library. Essentially, like, you can view it like a third client. You have a producer, you have a consumer, and then you have Kafka Streams, which is a producer and consumer library that offers fully featured stream processing APIs in Kafka itself. So it really builds on the primitives in Kafka to offer a very lightweight library that applications can embed and process data using stream processing APIs.
So if you have Kafka Streams, do you still need a framework like Samza or Storm?
Less so over time. So Kafka Streams, the goal is to address application development and provide a lightweight library. Over time, there will be integrations with Yarn and Mesos, and the goal is really to decouple the problem of stream processing from the problem of deploying applications, because there are that other space of application deployment and containers is moving as fast as stream processing. So you don't necessarily want to tie your stream processing system into one of those like Yarn. So if you had Kafka Streams, and if you had the integration with Yarn or Mesos or any other system, then you essentially would not require frameworks like Storm or even Samza.
What about Spark?
Spark is interesting. Like I said, this space is moving very quickly, and there's a ton of innovation happening in the stream processing space. So there is Spark, there is Flink, which I really like, and there's Samza and Storm. And the key difference between Kafka Streams and all these systems are really these are more like frameworks, and they attempt to manage the entire life cycle of your stream processing code. But the problem, what we've seen and experienced as part of sort of deploying Samza at LinkedIn was that really the space of application configuration and deployment is very specific to every application. And at any point in time in a company, you have probably all the different types of container and application deployment and configuration that you can ever have. So you can have Chef and Puppet and Yarn and Mesos in different parts of your company. So you really don't want your stream processing system to be a framework. What you want is the ability to design it like a library, so you can either embed it in applications or make it behave like a framework if you wanted to. So the difference between these systems and Kafka Streams is very fine and subtle, and it's essentially a library versus framework difference. And I'd be super excited to see how this space evolves, as I'm very encouraged to see a lot of innovation happening.
Well, one thing that's interesting is that in most of the areas of this ecosystem, there's from 5 to 20 players.
Yes.
When I was at QCon, how many different streaming framework talks were there? Every day you would hear about 5 different streaming frameworks. It's super interesting, super exciting.
Right. Yeah.
But with Kafka, there's not really. Kafka kind of, the dust has settled and people are using Kafka. Do you think that this is that a sign of things to come? Will the dust settle more, or are we doomed to have just a vast multiplicity of some of these other components?
That's a great question. I have to think about that a lot. And what I've seen is, and what I think will happen is, for any new exciting area of innovation, there's always a necessary chaos before the calm. And so what we are going through in the stream processing land is essentially that kind of chaos, where there will be a lot of innovation happening. There will be several different systems, and eventually there may not be just one, but there will be at least a couple that will emerge that will cover the entire problem set. So, and this is actually true not just for stream processing, but in general for a lot of infrastructure in the big data space, is that, early on for a new problem, there will be several systems, and over time the dust will settle, and we will have a couple of systems that cover the entire problem set, from data collection, storage, to processing, analytics, and reporting. And the reality is that, lower level problems like storage often have, fewer sort of solutions than higher level problems like processing and analytics and reporting. I think that Kafka, which is essentially the storage layer, will continue to probably, be just Kafka or maybe one other system. But as you go higher up in the stack of data problems, then you'll have a little more on processing, a couple more systems on analytics, and many more on reporting.
So what's going on at Confluent? Confluent is where you work. It's offers Kafka as a service. What is the product offering at Confluent?
Yeah, so at Confluent, our mission is really to help companies make the transition to real-time data in a big way. And for that, we're putting together a product which we are calling the Confluent Platform, that offers all the necessary tooling, monitoring, libraries required to use Kafka in an effective and easy manner. So, that includes REST APIs and clients to be able to send data to Kafka. It includes Kafka connectors to be able to send data from existing systems through Kafka. It will offer Kafka Streams, as well as monitoring and management tooling to allow you to manage your Kafka clusters and data. So along with that Confluent Platform, we offer, technical training, consulting, as well as ongoing support to help companies leverage Kafka in business critical applications.
So if somebody were, what is a prototypical potential customer of Confluent?
Kafka is such a general purpose sort of data flow mechanism that it is really applicable across the board. So Confluent customers could range from, consumer websites, retail companies, financial companies, banks, to media companies, gaming companies, and so on. Really, the problem we are trying to solve is that of data collection and data integration, and making it easier for companies to break down the silos that they have developed over time and have a single infrastructure to collect data and make it available to various applications.
So I think you've given the demystifying stream processing with Apache Kafka talk since QCon. Is that correct? Like you've given it again, or you've talked to other people about it?
I've given it at QCon only so far.
Oh, only at QCon. Okay,
Right.
Sorry. I thought I saw a tweet where you had given it again. Well, anyway, in any case, what were the interesting conversations that you had with people following that talk? Did you have any revelations from the feedback that people gave?
The feedback was that there is, an immense interest in stream processing. I think I was pretty sort of happily surprised to see that a lot of companies and a lot of developers are very, very excited about this sort of new hope that Kafka Streams provides, which is application development can be viewed more as stream processors. And initially I thought that is too hipster of an idea, but I saw that a lot of developers were very excited and wanted to use Kafka Streams. And the second thing was, there's just a lot of excitement around Kafka and whatever comes out of Kafka and Kafka land, which was exciting to see is that Kafka is so commonplace and used across hundreds of thousands of companies that people are at a point where they want to know what's next and how they can process data.
How is the open source community of Kafka evolving?
The open source community of Kafka is evolving very rapidly. We did a latest release a week ago, which was a pretty big deal. We had hundreds of contributors. We recently added a committer to Kafka. And so all across the board, there's a lot of excitement around client development and adoption. The number of downloads for Kafka grew 7 times just in the first 7 months of 2015. So overall, all across the board in open source community, there's a lot of excitement around Kafka.
Cool. Well, that sounds like a great place to stop. Neha Narkhede, thank you so much for coming on to Software Engineering Daily.
Thank you for having me, Jeff. I enjoyed it.